Hey everybody, we are getting into something known as Kepler's three laws. He was a philosopher, a scientist, think 1600s. And one of the things that maybe didn't set him apart, it's not like nobody else did this, but Kepler, not only did he philosophize and think about our place in the universe, but he took a lot of data. And so these three laws from Kepler really came from him making observations, writing down measurements for those observations, and using those measurements to come up with ideas for how things in outer space are orbiting. His laws focus on things orbiting like the sun, like how the Earth moves, Mars, Jupiter, etc. But they can be extrapolated. They can be applied to also other things in orbit, like planets orbiting other stars, okay? Now, in these three laws, there's a lot more technicality to them that we're probably going to get into. Like, especially for the first law, we are simplifying things a bit just so they suit our needs. So we're not going to go into as much detail as you might experience if you learn these things further in a future class, or you do some extra reading or researching online. But anyway, let's go ahead and get started, okay? Three laws for us to talk about. Kepler's first law is really a law that describes how objects orbit in terms of their shape, okay? The definition that, again, we're going to focus on, is it the most technical? Is it the most strict according to what he published? No, but it's going to get the job done, okay? Kepler's first law says that planets orbit in an ellipse. If you remember from geometry, you have like a perfect circle that has a constant radius. An ellipse is like if I took a circle and I stretched it out. That's what this is showing. I don't know, maybe this is planet Earth as it goes around the sun. It's not in a perfect circle, it's stretched out, it's in an ellipse. Now, to be honest, this is a bit extreme in that if we could actually zoom out and look at the Earth and trace its orbit, it actually looks very circular. A lot of the planets in our own solar system kind of look like they orbit in a circle, but that's not really true. All of them are actually a bit of an elongated, a stretched out circle. That's how things orbit. If we wanted to get a little more technical, and to be honest, if we wanted to include a little more geometry, maybe you remember something about ellipses in geometry where it has two things known as foci, or there's a focus here and a focus here. It's kind of based on how you draw this ellipse. We're not going to focus on this term. Also, technically, if you Google Kepler's first law, it's going to make a comment how like the sun is at one of these foci or foci, one of these focus points. It's not wrong, but it's not really something we're going to focus on. For Kepler's first law, we're really just going to look at how it says planets, they orbit things in an ellipse, okay? Now, one way we can actually see that is this GIF right here is representing us taking snapshots of our sun. So imagine we had a camera, we had it in a constant spot, we kind of had like sunglasses on the camera so we could actually take a picture, and once a month we took a picture, and we can see in this image how the sun sometimes looks bigger and sometimes it looks smaller, and that's just like how when things are far away they seem smaller, and when something's right up close it seems really big. Obviously the size of my hand is constant, but based on whether it's far or close, it appears in my eyes, in my view, to be bigger or smaller. That's what this is showing. Again, the idea, sometimes the Earth is farther away, like when it's over here, the sun is going to look smaller. Sometimes when planet Earth is over here and it's closer, the sun is going to look bigger. So we can get a sense of this, even though we can't really zoom out and look at the Earth, we can still kind of see that by looking at the sun over time. Okay? Anyway, that's the first law. The first law is the easiest of the three laws, I'm sorry to say. Kepler's second law. Kepler's second law is weird, okay? It is totally understandable if you feel like you are confused even after us going over this second law definition, okay? It really helps to see an animation. So here it's representing, like, let's say this is planet Earth or just any planet as it's orbiting around and around. It doesn't show it in this picture, but pretend the sun is right here. It does kind of show the sun here or whatever star we care about, but let's say the thing it's orbiting is right here. And as we watch, maybe you notice something. This planet is going a little slower when it's over here, and it's going a little faster when it's over here. And also, like, you kind of see these wedges in this animation. What those wedges are representing is kind of the chunk from one spot to another in a certain amount of time. I'm going to jump over to this image just because it's easier to show when it's stagnant, okay? We have kind of this blue chunk. Imagine what we're doing here is we're marking, let's say the planet's moving around like this. When the planet gets to here, I mark where it is. And then I'm just going to make up kind of a time. Let's say 1 month later. 1 month, bam, I mark where it is. And so these 2 points, it kind of make like this shape of pizza or like a slice of cake. This is a chunk of area. And then as that planet still moves, I'm just going to repeat. Let's say when the planet is here, I make a mark. And when the planet is here, I make a mark. What Kepler came up with is kind of a geometry thing. If we're looking at the same chunk of time, say 1 month, the planet is always sweeping out the same amount of sliced pizza. This area is the same for the same chunk of time. If this was 1 month to go from here to here, and we have this long but thin slice of pizza, when the planet gets over here, it also will trace out a slice of pizza, but it'll be 1 month from here to here. The pizza's not as long, but it is fatter. We have equal areas in equal amounts of time. That's super weird. But it's also the same thing here. When we're over here, we have this really long, thin slice. Over here, it's kind of a fatter, shorter slice. Those areas are the same. It's like me saying, like, the wedge of cake. You get the same amount of cake here as over here. Some are longer, some are shorter, but you have the same amount of cake in total. But the key thing is that's happening in the same chunk of time. Why? Why is that relevant? And again, here's just another image. Again, let's say like from here to here is 1 month. We have equal size pieces of cake. Now, it's a weird definition, sweeping out equal areas in equal time. This means something to kind of a normal person. Admittedly, Kepler's description was a geometry description, okay? That was his proof. But what this really means to the average person is what I have here in purple. If you're sweeping out equal areas in equal time, that means the planet is moving faster when it's closer to the sun. And I'll show you going back to this GIF here, okay? If I have equal areas in equal times, well, when I'm over here and I have this really thin piece of cake, this thin slice of pizza, okay, it must be going slower from those 2 spots right there. Over here, I'm getting a fatter slice of cake, a wider, though shorter, but a chunkier piece of cake. The planet is sweeping quicker, and you kind of see that when you watch this animation. It kind of almost really boils down to that equation we learned for velocity. We know velocity is based on distance and time. If it's the same time to move this little amount compared to this bigger amount, if I'm moving a bigger distance here in the same amount of time, I have to be going faster. That's kind of what this is based on. I know that's maybe not the most intuitive thing. I think I have one more diagram, or I guess I'll go back to this diagram. Again, let's pretend going from here to here takes the same amount of time as going here to here. Okay, same amounts of time. Here to here, same amounts of time. Well, if it takes the same time, but this path is longer, it's a larger distance. If I'm going a larger distance in the same amount of time, I have to be going faster. That's the only way this works. If I have 2 people take the same amount of time, but one person travels a greater distance, they must have been moving faster. So that's what that means in the simplest way. I'm going to go back actually, okay? So if I am sweeping out equal areas in equal time, yeah, that's what the technical definition is. To be honest, I would focus on this right here. What that concludes, what that means is very simple, and it probably makes sense, but planets, they travel faster when they are closer. When they are farther away from the sun, or whatever their star is, they go slower, okay? That's the main idea. Now, I went to this slide to use this diagram, but I didn't actually mention this. Those first 2 laws that I mentioned, both of them are describing one thing as it is orbiting. Kepler's first law says that this planet, Earth or Mars or Saturn, it travels around the sun in a shape that is a stretched out circle. That's an ellipse. Also, Kepler's second law says, let's pretend this is planet Venus, okay? Planet Venus is going slower when it's farther away. It's going faster when it's closer. This is very important. These first couple of laws are describing one object as it's going around, because our last law is very different. It doesn't describe one object. here's what Kepler's third law says, okay? And there's a new phrase, there's kind of a new term in here. We'll get to it. It says the time it takes to complete one orbit. Orbit is going around an object, like the Earth orbits the sun in 1 year, because in 1 year, the Earth goes all the way around the sun, okay? The time it takes to complete one orbit, it depends on the distance the planet is from the sun, okay? Time to orbit depends on the distance. This phrase, or these words right here, orbital period. I already talked about orbit. Orbit just means to go around for astronomical objects. Period is a word used to represent a specific time. And we maybe haven't used that yet in this class, but you're familiar with this because think of the phrase a class period. You know what a class period is. That's the amount of time for one class. So this is very similar. It's the time, the period of an orbit. It's the amount of time for, let's say, a planet to go around the sun or any other star, okay? Now, what are we relating here? It's relating period, time. It's okay if you want to say time. It's just the specific time of going around. But it's relating time to how far away we are from the sun. And this is what's crucial. We're comparing objects here, okay? For example, Earth is a certain distance away from the sun. It takes Earth a certain amount of time in this smaller circle here for Earth to go around. It turns out that's what we call 1 year. Mars is farther away from the sun. Okay, so if we kind of had a whole bunch of meter sticks and we measured how far away Mars is farther away. According to Kepler's third law, because Mars is farther away, it has more distance, that means it takes Mars more time. That's what the third law is saying. We can compare the time it takes to go around based on the distance. And actually, you could also go vice versa. You could do the opposite, okay? So the time it takes to go around the sun, it's based on how far away that orbiting planet is. And it's comparing different, let's say, planets based on their distance. The one thing that maybe you saw in this diagram is this AU. This is not something I am ever going to quiz you on if you're in my class. So I'm never going to ask you to define AU on a quiz or a test. But it is something that you might see in investigations or that you might see in further research or things online or textbooks, things like that. AU, it's just a distance, okay? The problem with astronomy is like the universe is giant. Even our biggest things that we use for distance, like miles and kilometers, the Earth is millions of miles from the sun. We're using giant numbers here. So instead, one thing astronomers did was they actually made up a whole new way to measure distance. And they said, let's just call the distance from sun to Earth 1. And they call that an astronomical unit. Not the most important thing, just you might see this. It's representing a distance, and it's just a way for us to not have to deal with numbers that are always in the millions or tens of millions or billions, because usually what we measure with grams and centimeters in the universe, those are teeny tiny, okay? But that's what AU is, it's just a distance. But anyway, the third law is comparing planets, okay? Again, highlighting, we're looking at different orbiting things. The law compares, say, Mars to Earth, or maybe it compares the moon to one of our satellites that orbits the Earth, or maybe it's comparing Venus orbiting the sun to Pluto orbiting the sun. So it's comparing different objects as they orbit. This is my last slide. I just gotta have a cheat sheet here where it compares the 3 different laws and kind of what separates them. And to be honest, also some things that means or that makes them kind of similar, okay? So the first law, it's all about kind of describing one object and it's focusing on the shape. That's the first law. The second law also is describing one object, and this is the kind of weird technical thing. The planet sweeps out equal areas in equal time, or what it's saying is that when an object, or when, let's say, Pluto is farther away from the sun, it is moving slower, it has a lower speed. When it's closer to the sun, it's moving faster. The third law, it is comparing 2 different orbiting things. So notice this bullet point right here is different from these 2. Okay, and what it is focusing on is how much time it takes a planet to orbit. And how much time it takes, it's based on how far away that planet is, or that thing that's orbiting the sun or star is. Okay, so that is an overview of Kepler's 3 laws. We are actually in another video gonna get a little more detail into Kepler's third law, but those are first the 3 more generally. Alright, thanks a lot for watching. That's the end of this video.